In 2013, there was 9,528 cases of tuberculosis in the United States. Each year, tuberculosis strikes wealthy and poor countries worldwide, creating a worldwide epidemic. Tuberculosis is one of the most deadly diseases known to man. Attempts at cracking the code have been made over the years, but little work has been done. This year, our team came together to give our input on a solution.
Dude, Matt, what are you doing?
Check out what I'm working on. We are studying the bacteria tuberculosis, also known as TB. TB is a mycobacterium. It also contains these properties: acid-fast rods, slow growth, eugenic growth, TCH resistance, niacin production, and nitrate reductase. There are many other properties also that our nanotechnology will be looking for. Here's an image of a normal bacteria cell. This bacteria cell will be surrounded by our nanotechnology as shown in this figure. Oxygen will not be able to enter this cell. The bacteria is dependent on oxygen, so the bacteria will die because it will not be getting oxygen to it. Our nanotechnology will have the ability to self-assemble. This means our nanotechnology will come together to form all the way around the cell. The carbon rings will bind all the way around the bacteria. This is how the so-called covering is made.
Mycobacterium has been traced back as early as 20,000 years ago. Mummies found in Egypt, India, and China have been linked to spinal tuberculosis, otherwise known as Pott's disease. TB was so prevalent in the Middle Ages that it was named King's Evil and was said to be cured by a king's touch. In the 18th century of Western Europe, TB struck poor city slums and took the lives of a staggering 900 per 100,000 people. Robert Koch was the first scientist to really shed light on this problem. His research on the organism's protein coding led him to a Nobel Prize in 1905. Our version of a cure to this massively drug-resistant organism will include preventing oxygen from reaching its cells, further removing the organism of its fatal qualities.
Nanotechnology is at the atomic level. That includes electrons, protons, and neutrons. Nanotechnology is smaller than the oxygen atoms. The nanotechnology is made of carbon atoms. This is why the oxygen can't enter the bacteria cell. The nanotechnology will attach itself to the cell. The cell will be completely covered with the nanotechnology. This will create a coating. Each nanoparticle will be attached together. It will form a ring structure around the entire bacteria cell. Thus, the tuberculosis cell will not be able to get oxygen. This will cause the cell to die.
10 facts on tuberculosis. In 2013, 9 million people fell ill to tuberculosis. A total of 1.5 million people died from tuberculosis in 2013. 360,000 of those people had HIV. 80,000 HIV-negative children died due to tuberculosis globally in 2013. Tuberculosis is the leading killer of people with HIV. The death rate due to tuberculosis has declined since the year 1990. Very common in Southeast Asia and Western Pacific regions in 2013. Multi-drug resistant tuberculosis is hard to treat. 480,000 people developed multi-drug resistance tuberculosis in 2013. 37 million lives were saved from 2000 to 2013 through tuberculosis diagnosis and treatment.
TB is a bacteria, meaning it can be spread through the air from one person to another. Coughing, sneezing, or even speaking can transmit this deadly disease. TB generally infects the respiratory system, resulting in suffocation of the human body system. The normal methods of treating TB include surgical procedures and antibiotics, although many TB cells are immune to antibiotics. Okay, so to give you a scale of what we are doing, here's a nanotechnology example. Let's say a nanoparticle is 4 nanometers in diameter. If you multiply that by 1 million, you get the length of an ant. If you multiply the length of an ant by 1 million again, then you get the length of the Indianapolis Motor Speedway. Therefore, a nanoparticle is 1 trillionth the length of the Indy Motor Speedway. I'll give you one more example. A human hair is approximately 80 to 100,000 nanometers wide. So basically, 1 nanoparticle is 0.005% of the width of your hair. Alright, so now you have an idea of what we're working with. The average length of a TB cell is 2 micrometers, which is equal to 2,000 nanometers. Our team will be using the latest nanotechnology to look for acid-fast bacilli. This is one property that distinguishes TB from normal bacteria cells. From there, we will insert the nanotechnology into the body of an infected patient. This technology will provide a carbon ring cover for the TB cell. TB must have oxygen to be functioning and living, so essentially we are preventing it from getting oxygen. This will cause the TB cells to die off.